Thank you very much for the invitation to lead this discussion session, which will be about the asymptotic analysis of Painleve equations of type 1 and 4. And I would like to present today a handful of distinct approaches. And to do that, I've asked some fellow researchers to join me and to present, briefly present their own approach to study the asymptotic of some solutions of the Painleve 1 and Painleve 4 equation. And before I start, I would like to dedicate to this discussion session to the memory of Andrei Kapayev, who was a master of the asymptotic analysis of Painleve equation. So the plan of this discussion will be as follows. I will give a very brief historic introduction to Painleve equation, the isomonodromic method. Then I will speak about Painleve first equation. I will present this equation and how it is related to the cubic oscillator. And I will, introduce somehow the WKB analysis of this cubic oscillator. I will do the same for the Painleve fourth equation. In particular, I will study a class of solutions known as rational solution of Hermite type. Afterwards, it was planned to have a short talk by Peter Roffelsen on Boutron course, but he cannot participate. And so we will. So after me will speak Robert Buckingham about the other type of rational solution of Painleve fourth equation, which are called. Oh. I'm sorry, I can hear some noise. Can you hear me?
Yes, it's Andrei Voros just joined, and he has sometimes a brief moment of issues. Sorry.
Okay, so and then Robert Buckingham will speak about the orthogonal polynomials approach to study the asymptotic analysis of rational solution of Okamoto type, and Peter Miller will study the same solutions via the isomonodromic approach. Eventually, Ovidio Costin will present some results about asymptotic analysis of the Painleve first equation without using any isomonodromic approach. And finally, this will take more or less 1 hour. If you would like, I have presented some topic to discussion, or just you can ask question to any of us or whatever. I mean, whatever comment or question you want to ask, to raise after the talk of Ovidio, we will be free to do it. So here is a very short history of the isomonodromic method of the Painleve equation of the asymptotic analysis. So I'm sorry for my handwriting, which is terrible. And I did this slide with the help of Alexander Ritz, who cannot be here, but of course is the person who knows the history of the isomonodromic method. Is the most knowledgeable scientist in this field. So to start with, the isomonodromic method is just as old as the Painleve equation themselves, because as it was already mentioned by Nalini yesterday, or the day before yesterday, the Painleve 6 equation was discovered by Richard Fuchs as the equation for the isomonodromic deformation of a scalar linear ODE with 4 Fuchsian singularities and 1 apparent singularity. Okay, and then soon afterwards, Garnier extended this approach to the Painleve equation 1, 2, 5, or 1, 2, 3, 4, 5, again as equation governing the isomonodromic deformation of a scalar linear ODE. But now one singularity is irregular, and then you have from 0 to 2 Fuchsian singularities, and one apparent singularity. Okay, since the papers by Fuchs and Garnier, one in French and the other in German, there is a nice paper by Okamoto in English, where you can find a list of all these equations and the corresponding Hamiltonians, and it's very useful paper. Now, this is about let's say a scalar, the isomonodromic deformation of scalar equation. But nowadays, it's like the Painleve equations are mostly studied as isomonodromic deformation of a matrix system. And this concept of isomonodromic deformation of matrix system was actually introduced by Schlesinger in the same year as Garnier. But the true connection with Painleve equation was just discovered many years afterwards, and fundamental works by Jimbo, Miwa, and Ueno, and Flaschka and Newell. Okay, and what about asymptotic analysis? Asymptotic analysis of Painleve, Painleve equations were studied until the 20s and then from the 70s on. So, but there was quite some works about asymptotic analysis of Painleve equation, and the first work were without using the isomonodromic methods. Okay, so if you think about the Boutroux work, which is of 1913, where he introduces the truncated solution of Painleve 1, for example. And then, so this was done without without using the isomonodromic deformation method. And also the asymptotic analysis of Painleve equation continued afterwards. When the isomonodromic method was already available, the non-isonodromic approach to the asymptotic analysis continued and continues today. And for example, there is, if you look in the book by Bender and Orszak on mathematical methods for engineering, there is a section on the asymptotic analysis of Painleve 1. Then, for example, you have the approach by Yoshi and Kruskal. There is a nice paper of Kitayer where he reviews the work of Boutroux. And then there are a series of papers by Ovidiu and Rodica and collaborators. Okay, this is like the non-isomonodromic approach we will spoken by Ovidiu. And what about asymptotic analysis with the isomonodromic method? Well, this was started by Itz in the early 80s, where he did some work on Painleve 3 already in 81. And then there were also all these Itz school, which some people in this school were, Shenov, Petrov, Kitai, and Kapaya. We did a lot of work on equation not Painleve 6. And then there is a famous work by Jimbo on the asymptotic analysis of Painleve 6, where he considered somehow the generic situation, and this work was later completed by Gutset recently. Okay, so what I will speak about is like studying asymptotic analysis of Painleve equations via the analysis of the scalar isomonodromic equation. Okay, so the question that I will study here in this couple of slides is the Painleve first equation. Okay, you see the Painleve first equation, it's a very simple equation. You can write it like in a scalar form or in a matrix form, which is somehow convenient for the isomonodromic method. Okay, it's like a very simple Hamiltonian equation, but the Hamiltonian depends explicitly on the time. And it is the isomonodromic, is this the equation, the Painleve first equation governs the isomonodromic deformation of the cubic oscillator, which is this scalar linear ODE of the second order. which, as you see, it is a cubic potential plus a Fuchsian singularity which is apparent. Okay, you see here this number 3/4. Okay, it tells us that the singularity is resonant, but the equation is made in such a way that it is really not only resonant but really apparent. Now, what does it mean isomonodromic deformation? It means that to the cubic oscillator, one can associate some irregular monodromy data, which are the Stokes multiplier. So here you see like the complex lambda plane. Okay, we call it C lambda. You can divide the complex lambda plane into Stokes sector. In every sector, you will define a unique normalized subdominant solution, which you would call psi k. And then the Stokes multiplier are some numbers that link together solutions defined in distinct sectors. Okay, so it is a, this is not too complicated, but of course I cannot explain it in a few minutes if you have never seen it. But if you have seen it, you have these 5 Stokes multipliers, which are not independent one on another because they live in a 2-dimensional manifold of monodromy data. And this manifold, for some people doing algebraic geometry, has a name which is the A2 quiver variety. Okay, the isomonodromic deformation method means that, so you see this Stokes multiplier depend on 3 parameters, which is P, Q, and T, the time. So they depend on 3 parameters and they live in a 2-dimensional variety, which means that there is a 1 dimension more. And the idea of the isomonodromic deformation method is that if you think of this Stokes multiplier as a function of the time, then they are constant if and only if these other 2 parameters, P and Q, as a function of time, satisfy the Painleve first equation. Okay, this fact means that there is a map, a Riemann-Hilbert correspondence or a monodromy map from the space of solution of P1 to the A2 quiver variety. And in fact, this map can be proven to be bijective. Okay, a proof of this fact is in a paper of mine of 2010, for example. Well, it is, I just want to mention en passant that that the space of solution of Painleve 1 has a very nice algebraic structure, and also the A2 quiver variety has a very nice algebraic structure. But the Riemann-Hilbert correspondence is highly transcendental. So the 2 varieties are holomorphically equivalent, but they're not algebraically equivalent. Now, let me study, let us suppose that I want to study the poles of a solution of Painleve 1. And you know that we have just seen that solution of Painleve 1 are fully characterized by 5 numbers, which are the Stokes multiplier. And then we have this result from 2010, which says that the point A in the complex plane is a pole of the solution of the Painleve first equation, if and only if there exists another point B in C, such that the Stokes multiplier of this cubic oscillator without apparent singularity coincide with the Stokes multiplier associated to that solution. Okay, so it means that if we are just interested in studying poles, we can forget about this apparent singularity. Now, suppose that I want to do asymptotic analysis of this problem. So the way that you do asymptotic analysis on an equation like a cubic oscillator is you do complex WKB method, whose result is a way to approximate Stokes multiplier with the exponential of some abelian integral. So an abelian integral will be these things here. It is the integral along a cycle of an elliptic curve naturally associated with the potential. So this curve, I call it X. But then, you know, we have 5 Stokes multiplier. We have an infinite number of cycles because the homology group of an elliptic curve is Z2. And so one man must understand which Stokes multiplier associated to which cycles. And this actually depends on something which is the topology of the Stokes complex, which I will show in an example in the next slide. And then if you want to do asymptotic analysis, then you need a big parameter, which a priori is not given in the Painleve equation. And that big parameter, which is exactly 1 over h bar, if you this is like the h bar that it is used in the exact WKB method, will be this combination a squared plus b squared over plus b squared to the 1 over 6. Now let me specialize further. Now suppose I'm in, excuse me?
B square or B cube?
Yeah. Yeah.
Which is the correct one? Because you were saying a squared plus b squared, but then
no, b cube, b cube.
Okay.
Yeah.
Okay.
It could be the converse, but I'm almost sure that it is correct. But I will check.
Okay. Thank
you. So if I want to specialize further and I want to study, let's say, a special solution. Now, special solutions are associated to special points in the monodromy manifold. For example, the Triton-K solution, which is the most special solution of the Painleve first equation, it is related to the monodromy data describing the vanishing of 2 Stokes multipliers, which in turn means that 2 quantization conditions are satisfied. So if we look to the T-plane here on the left, and these dots will represent more or less the pole of the Triton-K solution. Okay, this is called Triton-K solution. It's so special. The poles are just in this sector. Then on the lambda plane, this solution corresponds.
Excuse me. Sorry. Yeah. Is it the discriminant of the curve, the large parameter that you take the 6th power of? Sorry.
Well, yes.
So then it will be a cubed.
Okay. If you take
the a cubed plus 27 b squared, then or something, isn't it?
Yeah, exactly. I mean, whatever things which has a cube and b squared or the point.
Yeah,
yes.
a cubed plus 27 b squared. Yeah. Okay.
Okay.
Sorry.
So, like,
I just
no, it's perfect. Like, if you want to think like in terms of moduli space of elliptic curves,
yeah,
then you fix the moduli or modulus, I don't know, and then you want to move with the fixed moduli, and so you have to take like the discriminant as a big parameter.
Yeah. Thank you. Thanks.
And so now, what is the WKB? As I told you, now we want to somehow approximate Stokes multipliers by exponential of abelian integral. And as I told you, we need a way to associate to elements of the homology group a Stokes multiplier. Now, for this particular solution, the answer is in this slide. So you have to look for elliptic curve, which are called Butler curve, where let's say the graph made of the union of all Stokes line is connected. Okay, and then this gives you a way to select two cycles, which I call gamma 1 and gamma 2. And approximately the solution of this, so the poles of the Painleve first equation are given by this couple of numbers, A tilde mn, B tilde nn, which are solution of this pair of Bohr-Sommerfeld conditions, which were the same condition that Boutroux wrote in 1913. Now, the theorem says that if these numbers, m plus n, are large enough, so if m plus n is large enough, then there exists a unique pole, Amn, of the Painleve Tretinoquet solution, which is close to this approximate pole, A tilde Mn, and close is by this exponent. Okay, now, a few comments of this. So in these papers of mine, which are a bit old, I just consider poles and special solution, but this is not really a limitation of the method that I use, but just of my interest and abilities at the time. For example, in a recent preprint, which is the appendix of the paper by Bridgeland, I computed the Stokes, the asymptotic of the Stokes multiplier for regular value of the solution of Painleve equation, which means with apparent singularity. And by the way, this is not the only way available to do this kind of analysis. At the time that I wrote my paper, there was already a thorough asymptotic analysis of Painleve 1 by the matrix isomorphic method by Kapaev and Kitai. It was published in the Letter of Mathematical Physics in '92. Then there were a lot of non-isomonodromic methods available too. But the message, it is okay to reproduce previously known results using a new method, because this new method can later be used to attack and solve the problem, like I did. I will show it in the next slide. Computing an unknown asymptotic, which was the one of the rational solution of Painleve fourth of Hermite type. And then some formula that I used in my paper then was later used by Bertola and Tofvis and by Bridgeland in very different in different topics. So I mean, it is good if you reproduce the same result with new method. Now let me go rapidly through to Painleve fourth equation. I will not write down this equation because it is too complicated to write down, but the associated oscillator is pretty simple. You see it here. It's a harmonic oscillator with one Fuchsian singularity at the origin, and again an apparent singularity somewhere in the complex plane. Now, the monodromy manifold of this equation is more complicated of the one of the Painleve first equation, because of the presence of the Fuchsian singularity at the origin. So you can have a generic singularity, you can have a resonant singularity, you can have a resonant apparent singularity at the origin, and this split somehow the monodromy manifold in different pieces. And that's why the construction of the manifold and the Riemann-Hilbert correspondence is more complicated. But we did some work on this together with Peter Rothesen. Is published in Sigma, but based on previous work, for example, by Kapaev. Now, Painleve equation admits two families of rational solutions. I think, well, Robert and Peter will speak about it later, about the Okamoto type of solutions. And Peter Clarkson will give a talk about rational solution. Now I will briefly speak about the Hermite type of solutions, which can be written in terms of some polynomials, which are called generalized Hermite polynomials. These generalized Hermite polynomials are Wronskian of standard Hermite polynomials. And Clarkson, in 2003 or 2, I don't remember, observed a very regular pattern of the roots in the complex plane of these generalized Hermite polynomials. And he asked how it was possible to explain this phenomenon. And in this paper with, in two papers with Peter Rothesen, we give somehow an asymptotic answer to this observation. And the starting point of this of our work is again the fact that this rational solution corresponds to very special points in the monodromy manifold. And in fact, we arrived to a similar characterization of the poles of these of the roots, the roots of generalized Hermite polynomials. We have a characterization of the roots of generalized Hermite polynomial very similar to the characterization of the poles, of the three-truncated solution. So we fix M and N, which is, so we fix a generalized Hermite polynomial, and we have the theorem. We say that the point A in C is the root of the polynomial if and only if there exists another point B in the complex plane such that this harmonic oscillator satisfies two properties. Now, the first property is that the solution, the singularity at the origin is apparent. And the second condition is the existence of a solution of the boundary value problem, which is a quantization condition. Exists a solution which vanishes at infinity at 0. Now, again, so together with Peter, we have analyzed this problem in two different regimes. One is the regimes where you fix the parameter m and you let the other parameter m to go to infinity. And the second regime is when both go to infinity, but the ratio is fixed. Okay, these are technically very different problems. Okay, so the first problem is not really a WKB problem. It is it's a strange connection problem between a function, a solution which is approximated by Whittaker function at 0, and another solution which is truly a WKB solution at infinity. And you have to do some matching, and we find and prove an explicit asymptotic formula for the roots of this Hermite polynomial in this asymptotic regime, which, by the way, corrects a previous conjectural formula by Felder, Emery, and Veslow. On the other side, when we do the other limit, where both m and n go to infinity, then we arrive to a pure WKB, let's say, regime. And it boils down, let's say, after quite some work, because the paper is incredibly long, it's 70 pages, again, to a pair of Bohr-Sommerfeld conditions, which are really just like the one for the three-truncated solution. Just that the meromorphic differential that we are using is another one. But again, we have a Boutroux condition, and we have this pair of Bohr-Sommerfeld quantization condition, and then we have exactly the same result. So if we have a solution of this semi-classical quantization condition, then close to this solution, we have a true root of the generalized Hermite polynomial. Now I want to show you some picture briefly. No, well, I should have not done this, but how do I compartilhar tela? No, I want to show you some pictures, which is okay. I don't know what it froze. Okay, yeah. So this is the first asymptotic regime. Now n is fixed, is equal to 5, and m is already 40. And you see these red dots are the result of the asymptotic analysis, and the blue dots are the true roots of the generalized Hermite polynomial. And the other picture that I want to show you is in the other regime, which is when both m and n go to infinity. Okay. And it's pretty amazing because in the true roots of the generalized Hermite polynomial are the blue dots, and the asymptotic result would be like the points in this slightly deformed lattice, but you cannot see any difference. Essentially, it's the asymptotic. The asymptotic is extremely precise, and I don't know why it is so precise, but it is a fact. Okay, let me go back to my presentation. So I want to finish with a few comments. So the first comment is that whichever Painleve equation one considers, if you're doing asymptotic analysis of the scalar isomonodromic equation, then you are led to the study of anti-Stokes lines or Stokes line of a meromorphic differential on an elliptic curve. Okay, it's always an elliptic curve. The only things that vary with the Painleve equation and its parameters is the differential that you have to consider. The second message is that there is an important class, which is still unclassified, of special solution which lead to the study of Boutroux curves, which are algebraic curves with a meromorphic differential, such that the integral along any cycle is purely imaginary. And the third message is that even though the matrix and the scalar equation are gauge equivalent, okay, geometrically you are led to think in two quite different ways, because, for example, if you are considering the matrix equation, then your matrix is a connection on a trivial line bundle, and your function psi, solution psi, will be a trivializing connection. While you think in terms of scalar equation, then your object Q, which is the potential, is a projective connection. And geometrically, the object you want to study is a ratio of two solutions, which is called a developing map. Okay, on my side, I finished, so I think it's time for Robert to speak about rational solutions of Okamoto type via the orthogonal polynomial approach. Thank you.
Hey, thank you. Can you see my screen? Hello?
Yes.
Okay, you can see. Okay, excellent. So yeah, thank you first to Davide for the invitation to participate in this very interesting session. And it's good to see so many friends and colleagues. So yeah, just very briefly, I want to talk about the result that was alluded to on Davide's previous slide there. So I'm actually going to be talking about the Hermite polynomials because the approach I'm taking here, as near as we know, cannot be applied to the Okamoto polynomials, which is an interesting fact in and of itself. And so this method was developed by Bertola and Botner for the Painleve 2 equation and for the Jablonski-Vorobev polynomials associated to them. And then I extended it to the generalized Hermite polynomials and rational solutions of Painleve 4. And so, like I said, we don't think it can actually be applied to the generalized Okamoto polynomials, but I think the takeaway is that it's still an interesting connection to some things that you might not expect to show up in Painleve equations, and so it sort of shows the richness of the area, connections to lots of different things. So let's see, I need to try that. Okay, so here's the Painleve 4 equation, and the things I'll need are that there are certain parameters, alpha and beta, right? So you vary those, you get a different Painleve 4 equation, and you only get rational solutions for certain values of alpha and beta, okay? And I'm going to be focusing on the particular choices of alpha and beta when you get generalized Hermite rational solutions. And there are others that Peter will talk about that lead to more, a little more interesting behavior called the generalized Okamoto polynomials. Okay, so just in case you haven't seen them before, here's how you generate the generalized Hermite polynomials, okay? It's a 2-parameter family of polynomials indexed by m and n, and if you reduce to n equals 1, then you get the standard Hermite polynomials. And they're defined by this recurrence relation, okay, one that increments m and one that increments n, okay? And one thing that we'll need for this approach is that the standard Hermite polynomial has a nice generating function, okay? That's really the crux of the matter here. It's the lack of this generating function that makes it difficult to deal with the Okamotos using this method. So once you have the specific parameters, then you build your generalized Hermite polynomials, then you take a ratio of 2 successive polynomials and take the logarithm, take a derivative, and then you get a solution of Painleve 4. All right, and there's 3 distinct families. Okay, and so here's some more pictures of the poles and zeros. So I'm specifically interested in or rather the paper I wrote was specifically interested in the second case in Davide's presentation, where we're keeping the m divided by n ratio fixed. And so if m equals n, then you get squares. And if you scale them, they seem to form, they seem to densely fill a particular region of the plane, the complex plane. And then if you set m divided by n to be, say, 2, then you'll get this aspect ratio it's kind of like 2 to 1, right? You can count the poles. Okay, the poles form this m by n grid, but it's not quite a square, and it's this deformed curvilinear rectangle. And so just very briefly, these are these rational solutions show up in various applications, especially in nonlinear wave equations, but also in exceptional orthogonal polynomials and Coulomb gases. So, okay, so this is the key slide. And so all the math is, well, most of the math is on this slide. So how are we going to study these using orthogonal polynomials? So you start with your Painleve 4 solution. Okay, that's a step 1, associated generalized Hermite polynomials. Now, what we do is we take remember, we know that HK, the Hermite polynomial has a generating function. And we use that fact, which I'll show in a second, to write the HMNs, the generalized Hermite polynomials, as a Hankel determinant. Excuse me. Okay. Then, okay, so now yeah, it's a Hankel determinant of the Hermite polynomials. Okay. Now we're going to use the fact that, now we're going to use the fact that we have a generating function to re-express the Hermite polynomials in terms of a moment, okay, moment of a certain measure. And now we've got a determinant of moments, and so that leads us to orthogonal polynomials. Okay, that's step 4. Once we have orthogonal polynomials, then we can study them by our method of choice. For example, we could construct the Fokas-Katajevic Riemann-Hilbert problem, and then we could use the Daishio nonlinear steepest descent method, which is the approach I took. Okay, so just fleshing out each of those steps, just very briefly. So we start with the standard Hermite polynomial, and then it was a result of Kajiwara and Ota and Nomi Yamada that the HMN, okay, the generalized Hermite polynomial, is up to this scalar factor here, a determinant of a matrix whose entries are entirely the regular Hermite polynomials. So then what we do is we go through a couple steps and we use the Cauchy theorem, and we take the non-generalized, the ordinary Hermite polynomial, and apply some complex analysis to it. And we get out the fact that HM plus J can be written as this particular moment. See, it's the jth moment with respect to the measure nu, okay? And nu is given up here, and nu depends on M, and it's the jth moment, okay? And that's what we'd like to get to orthogonal polynomials. So this is just, right, so what we would like to get orthogonal polynomials is a particular matrix of, particular determinant of a matrix of moments. However, they're not, you have to shift them to get them from the Kajiwara-Ota result to the Painleve, what you need for the Painleve equations. So we prove a little lemma here, Hankel determinant identity. Okay, and then we take that measure nu that we had and form orthogonal polynomials from them. Okay, and so for example, now we can, if you remember this ratio here, this was related, the ratio of determinants, right, was related to the up to a factor. It was, well, and then you take a logarithm and a derivative. That was the solution we were looking for. Okay, and so it turns out that information is encoded in this normalization constant for the orthogonal polynomials. Okay, so I know that was several several steps that go by very quickly, but the upshot is we can take those rational solutions of Painleve A4 and we can come up with orthogonal polynomials that allow us to extract information about them. And this is great because orthogonal polynomials can be studied by a variety of different methods. Okay, so here is an example of a result that we proved using this method. We found the specific formula for the boundary curve, and I'm just writing it down here just to show you it's completely explicit. All you have to do is solve a cubic equation, quartic equation, yeah, because there's 4 corners, so quartic makes sense. And then when you plot the boundary predicted by the asymptotics, it matches up very nicely with what we observed. Okay, and here are some plots for other aspect ratios. Okay, other m divided by n ratios. Okay, and so I think that's all I wanted to say, but here are the two references. The Bertola-Botner approach that was originally done for Painleve 2, and my result on Painleve 4 for generalized Hermite. So thank you.
Thank you. So now it's Peter Miller.
Okay.
Time.
Okay, can people see my screen? Is it okay? Great. Well, hi, everybody. And thank you very much to Davide for the invitation. Also to Robbie for presenting the material about this orthogonal polynomial method. So I would like to discuss another approach that reproduces, again, many of these results that we've heard about already. It also touches on this generalized Okamoto case for Painleve 4. So this is the isomonodromy approach. So let's just get started. So this approach is based on the matrix lax pair for the Painleve 4 equation. Everything I'm saying actually applies to many other equations as well, but I'm going to illustrate things in the Painleve 4 case. So this is the lax pair here for the Painleve 4 equation. It consists of two simultaneous matrix differential equations, linear matrix differential equations on some unknown psi with coefficient matrices lambda and x, okay? And this lax pair was written in this form in a paper of Jimbo, Miwa, and Ueno, but you can also find it in this book of Itzin, Kapayev, and Fokas and Novokshchenov. Okay, so the point is that this overdetermined linear, simultaneous linear system is compatible if the following nonlinear equations hold true on these coefficients y, z, and u. And we'll identify this last equation on u as the Painleve 4 equation with parameters theta 0 and theta infinity. So whenever these equations hold true, you can solve these two linear equations simultaneously. There's a common fundamental solution matrix psi. That's the key thing we're going to use. Okay, so when we think about the this situation of these generalized Okamoto polynomials, Robbie mentioned the special values of parameters. And there's a crazy picture here. This is the theta 0, theta infinity plane, many dots in this plane. The circled dots that you see in this picture, the ones that have unfilled centers, those are points. I don't know if you can see them. Can anybody see a dot with a hole in the middle? Yeah. So those are points in the diagram where one has a rational solution of generalized Hermite type, and then all of the other dots, the ones that have their centers filled in, they're all over the place in the picture. Those are the parameter points for generalized Okamoto rational solutions. So they satisfy this kind of quantization rule on the parameters theta 0 and theta infinity. Now, there's a special point in this picture as far as we're concerned. That's the red dot here at the center. It's not really at the center of the coordinate axes, but it's the center of the diagram as far as Okamoto is concerned, because that's the seed solution. So if you take theta 0, theta infinity to be 1/6 and 1/2, then there's a unique rational solution of the Painleve 4 equation for these numbers, which is just this function here, this linear function minus 2/3 x. So we regard that as the seed solution for the generalized Okamoto family. Now, let me just describe the approach. You know, it's time to be planting the vegetables in the garden. And so I'm motivated to think of it this way. There's kind of two steps to the procedure, okay? First, you sow the seed, you plant the seed. For us, that means that we're going to take the special parameter values here and the special solution of the Painleve 4 equation, and we're going to solve the lax pair. We're going to find the simultaneous solution matrix for that lax pair. And in this situation, the point is this is a simple function of x, and consequently, it's going to be the x equation that plays the fundamental role here. Usually, in isomonodromy theory, one thinks of as specifying initial conditions and studying the lambda equation, the spectral equation, as the fundamental scattering problem, if you like. But here we're going to focus on the X equation because this is a simple function. And that's really the utility of dealing with the seed, planting a seed instead of transplanting an entire grown plant. Okay, so anyway, so we're going to compute the relevant monodromy data and formulate the inverse monodromy problem as a matrix Riemann-Hilbert problem. And then we will later on reap the harvest. And the idea here is to apply these so-called isomonodromic Schlesinger transformations, and those have the effect of incrementing or decrementing these integer lattice parameters. So they're going to move us from this point in the lattice to some other points in the lattice in little steps. And those little steps have very little effect on the data for our Riemann-Hilbert problem. So consequently, we're going to be able to write the Riemann-Hilbert problem for any point in this lattice. And because every one of these Schlesinger transformations goes with a Becklin transformation of the potential U of X that solves Painleve 4, from the structure of that, we can tell that we're getting a rational solution of the problem, okay? So that's the basic idea. Let's go through the steps quickly on the details a little bit. So to sow the seed, we're going to take our special seed value parameters here and our special seed solution. And remember, there's a differential equation for y of x, and we can solve that in closed form here and write this as the solution. So we have u and we have y, and we also therefore have this z function, and we dump that into the x problem of our lax pair. And now that problem looks like this. It's a lot simpler to look at. It's not too bad at all. And if we just make a simple gauge transformation, this is really ARA's equation for the first row. So we've reduced the problem to classical special functions is the point. So here we have ARA's equation, and we're going to take for it just a general solution in terms of AI and BI of this combination variable W. And we're going to have coefficients, of course, in the linear combination. And those things have lambda dependence that has to be determined from the second equation in the lax pair, the usual spectral equation. But because we've already solved this, because we've solved the x equation already, and we know that this function u of x makes the lax equations compatible, then we can solve that lambda equation explicitly and determine the lambda dependence of these coefficients. So that's not difficult at all. And that means that you know the general simultaneous solution of the lax pair for the seed. Once you have that, what you have to do is build canonical solutions. And Davide mentioned how this goes as well. So there are 4 Stokes sectors in the lambda plane for the problem. And in each one of them, one constructs a solution that has this kind of asymptotic behavior at infinity. And then there's also a solution near the origin, and it has the feature that if I multiply by this diagonal matrix, I get something analytic at the origin. So those are 5 solutions, and of course, they're all related by constant matrices, multiplication on the right by constant matrices. So the ones in the Stokes sectors are connected by Stokes matrices that are defined in such a way. And then we can go from the sectors to the origin by connection matrices that are defined relative to the solution at the origin. So anyway, all those matrices can be written down explicitly because we have these psi's. And so here is just a sample of what these matrices turn out to be. Okay. So turning this back around, what we have is a Riemann-Hilbert problem on the inverse side. So we may peel off this exponential factor and write a matrix Y of x lambda. And it satisfies the following Riemann-Hilbert problem where the parameters theta 0, theta infinity are the special numbers here. So we're looking for a matrix Y of lambda x. It's a function of lambda depending parametrically on x. And it should be analytic in the complex plane. Take away that contour that was shown on the last slide. It satisfies a jump condition conjugating these connection and Stokes matrices by some exponential conjugating factors on every arc of this jump contour. This product should be analytic at the origin. That was a property of the psi 0 function. And then at infinity, when we peel off a power, we're going to have convergence to the identity. So that's supposed to define this matrix Y given these matrices over here. And from the solution of that Riemann-Hilbert problem, you can pull out a function u of x by looking at the various matrix elements and taking the right kind of limits. And that does indeed produce the thing we put in at the beginning, minus 2/3 x. So in some way, we put this in, we turned it around and got it back out again. But now we're going to move to the next step and try to reap the harvest, okay? So in this step, we observed that the very same Riemann-Hilbert problem, but now formulated for general parameters in that generalized Okamoto lattice, encodes by exactly the same reconstruction formula unique generalized Okamoto rational solution of the P4 equation. And that's because the fact that this function here, this U of X function, solves Painleve 4, that's a really soft argument. It's based on the dressing method. It has nothing at all to do with these V matrices that we built in the first step. And then the second thing is that the points of the parameter lattice for generalized Okamoto solutions, they're generated from the seed by this kind of Z2 action. It's a Z2 lattice, really. And the generators increment these thetas by 1/2 or decrement by 1/2. So there's kind of 4 simple generators. Now, each of those generators goes with a Schlesinger transformation. And what that does is it takes the solution of the Riemann-Hilbert problem for a given parameter pair into that with exactly the same monodromy data, the same V matrices. It just changes the indexes here, these 2 parameters by steps, okay? And that's done by multiplying on the left by some kind of gauge matrix. So for example, if we want to move in the upper diagonal direction in our lattice, we want to increment both of these by 1/2, right? Then we have this gauge matrix like that, which is going to do something at infinity by this lambda to the 1/2. It's going to shift the theta infinity up by 1 because of this, and it's going to bring down the theta, or also boost the theta 0 by 1 because of this negative 1/2 power at the origin. So anyway, this takes a solution. This takes a solution Y into some new solution of the same Riemann-Hilbert problem for shifted parameters. And if you look at what that's doing to this formula for U, you see that this new coefficient, U upper arrow X, is written in terms of the old one and the old parameters by this kind of formula. This is like the Gromach transformation formula. And what it really is it's the Becklin transformation that goes with this Schlesinger transformation. And obviously, if you plug in a rational function for U here, you get a rational function for U up arrow out. And that's why we're getting the rational solutions of the problem in this lattice lambda GO. Okay. So some basic properties of this method, just to kind of wrap it up here. So it's applicable at least to all the known rational solution families, excuse me, for the second, third, and fourth Painleve equations. And I think it's certainly applicable to the others as well. We just haven't tried it yet. The starting point here is the lax pair and a simultaneous solution matrix for the seed solution. And that is expressible in terms of classical special functions because we're leveraging the X equation. And this is really in contrast with the usual approach in isomonodromy theory, where you focus instead on the lambda equation. It doesn't rely on specialized representations in terms of polynomials, determinants, or Wronskians. And mainly it gives results for the rational solutions themselves rather than for the special polynomials. That's because this U function is really the primary thing. And then it leads to a Riemann-Hilbert representation of the rational solution. And I'm not going to have time to go into this, but it really makes available a whole toolbox of techniques for asymptotic analysis. This Dave Joe steepest descent technique is the fundamental one, really, that allow the rational solutions to be analyzed when the parameters are large, okay? So here are just a couple references. So this is a paper with Robbie about the Painleve 4 rationals from last year. These are some steepest descent papers from Dave, Joe, and Benakides. Then, of course, there's the main reference here is this textbook, reference book by Fokas, Kapayev, and Novak-Shenov. The Schlesinger transformations can be found in this paper of Fokas, Mugan, and Ablowitz. And then there's a paper here by Novak-Shenov and Shishel Konagov, I'm sorry, where the seed was planted actually for the case of the Okamoto polynomials as opposed to the generalized Okamoto polynomials. Okay, so that's my presentation. Thanks.
Thank you very much. So now we shift completely approach, and it's time for Ovidio's presentation.
All right, can you see and can you hear me? Okay, all right. So, so this would be an extremely brief presentation. I called it a satellite view of what one can get just through resurgence. And I mean, through these 4 slides, there will be very little math because I focused on the main ideas, which I think are simple. So the 3 topics are: 1, the technique, which is new, the transasymptotic matching technique. I'm going to talk about the proof of the Dubrovin conjecture using resurgent methods, and separately, how to get explicit connection constants and formulae using just transseries and asymptotics. So this is very much up the alley of this general meeting on resurgence. Okay, let me put it in presentation mode. Sorry. Okay. So this should be better. Okay. The bibliography is in preparation. I'll put it later. All right. So first, about the transasymptotic matching. So this is the technique that we introduced in Invenciones in an Invenciones paper with Rodica, 2001. And this works for any summable transseries. Let's focus though on the truncae or 3 truncae of P1. So this is our P1, the normalization. And in resurgence, you have to go to the so-called Descartes critical time. People familiar with Painleve would not find this territory unfamiliar. This is just the Boutroux form. So you go to the Boutroux form. And then the solutions, the general solutions, have transseries, which are Borel summable. And here I would like to think of them as functions of 2 formal functions, still of 2 variables, 1 over x powers of x, and the exponentials that I consider a different variable psi. Psi is the constant, free constant, x to the minus a half correction, e to the minus x. And this should be to the power k, and it isn't, but okay. Here it is. So the thing is, only the x part needs Borel summation. If you do that, you end up with an actual function, which is the solution. In this case, is the 3 truncae. And I want still to think of it as a function of 2 variables, 1 over x and psi. So after this Borel summation, I'm dealing with a function which is analytic in x and it's analytic in psi. If I focus on the psi part and I would write a power series, that would have a disk of convergence of a radius that turns out to only mildly depend on x if x is sufficiently large. Among other things that we proved in that paper, and it's much more general than P1, of course, we proved that the solution itself must have singularities somewhere on the boundary of the disk of convergence. This is very similar in principle to Abel's theorem in complex analysis, and here you should get double poles. Now, since this variable is essentially e to the minus x, which is periodic of period 2 pi I, these poles are with necessity nearly periodic. Okay? And we show in that paper that for all first and second order ODEs and many more systems, the position of the singularities, their asymptotic behavior can be calculated basically cheaply in closed form to any number of orders, and I put some of them for Painleve P1 in this Boutroux variable. Some expression, don't worry about it, in terms of the constant, okay? Now, the important thing for the rest is that if x is not too small and you keep a few number of powers, you truncate this series, both in x and in psi, this results in a highly accurate representation of h, not only throughout the domain of analyticity, but also in part of the pole region. In fact, you can cover any fixed number of these nearly periodic arrays of poles. So that's the core of the technique, one of them that is in that Invenciones paper. And next in line is the Dubrovin conjecture. So this is a central connection problem, infinity to 0, which was open. Here is what it says, that the 3 truncae is analytic in the full sector, where it is asymptotically analytic, all the way to the boundary, all the way to 0. Beyond this sector, there are poles. Okay? So this is based on a Duke Math Journal paper that we published with Min Huang, he was my student, at that time in Sartanvia. I mean, the idea is really simple. What do? We use a few terms of the double expansion that I showed above, because in general, to represent the tree truncae throughout its domain of analyticity, and for all z which are sufficiently large, which for Painleve turns out to be 3/2 is sufficiently large to get an accuracy of 10 to the minus 2 with few terms. Step 1. So we have control all the way to the boundary, all the way almost to 0. What next? Well, somewhere at a point of absolute value 1.5, we match that to a Chebyshev polynomial approximation of the solution of degree 7, by the way, not a big deal, just by matching them. And the Chebyshev polynomial is valid on a line that goes from that special point down to the origin. And that polynomial basically preserves this accuracy of 10 to the minus 2. Okay? Last step, so now you have the value of the function and of the derivative at 0. Then what? You have a Maclaurin polynomial at 0. It satisfies the recurrence relation that you can calculate based on P1. And you can estimate the radius of convergence. And it turns out that the radius is greater than 1.5. In fact, it's 2 point something, never mind. But 1.585 is greater than 1.5 that you have covered already, and you're done. So that's the proof. Okay. So this appeared in Duke, as I said. I'll give references. I don't have them now precise. Okay. Something completely different. Now, suppose I want to do the following thing. I take the tree truncae of P1 or other tree truncaes for that matter, and I want to calculate Stokes constants in closed form. And the idea again is very simple. So the tree truncae, wherever you want to start it, has as a trans-series the pure power series with constant 0. Of course, it doesn't stay 0 throughout its domain of analyticity because you cross Stokes lines. Where it changes, and the way it changes is through this Stokes multiplier that I want to determine, okay, based on that. Here are some key observations, but let's first take a notation. Take X naught, some large point where you enter the pole sector. Evidently, and important note, there is a unique tree truncae up to the 5-fold symmetries. Hence, there is a unique mu, so that the pole width sector in Z is 2 pi over 5 and no more. Hence, if I go for an explicit asymptotic expansion of H through the pole region, then I must end up with an explicit equation for mu, which should have a unique solution. So now, through this trans-series mechanism, we reduce the calculation of mu to an asymptotic challenge. And this challenge is a multi-scale question on steroids, I called it, because there are poles, and because if you forge ahead with a 2-scale expansion, that's an incredibly long approach. That's very nice. Instead, we used adiabatic invariance, and we introduced 2 new ideas, 2 new methods, which are, you're probably familiar with 2-scale expansions. These are basic. 1, eliminate the singularities, eliminate the poles. How do we do that? We do that by a hodograph transformation. Take H, the function itself, as being the independent variable. Take X and the energy of elliptic functions to be 2 dependent variables. And you have a system of 2 ODEs, because that's what you started with for X and H. What does H do? H goes on cycles which are essentially Boutroux cycles, over and over and over and over. until you go from one side to the other of the pole sector. And X advances and S changes. All right? Second step, eliminating the fast evolution, which we do in a completely different way. We analyze, instead of this differential system, the Poincare map, which is what happens after one cycle. That satisfies a discrete evolution, which turns out to be very slow if you choose these variables. It's a slow evolution in the number of loops, okay? And this can be expanded, the difference equation can be expanded asymptotically as a series of ODEs in powers of 1 over x naught, your entry point, okay? So the constant of motions of these successive ODEs are the adiabatic invariants for the Poincare map, and if you have the Poincare map, you're done, because the evolution in one loop is completely trivial. So you have full control of the solution. Okay, good. So now, last slide. I just wrote down two invariants of this evolution. So this is the first one. This is the ratio of two hypergeometric functions. N is the number of loops. Kappa naught is the Wronskian of these two guys. X naught is your point of entry far away. And J is the same as this one. S naught is the initial entropy. Here you have the Stokes multiplier. Here. And then simply the product between position and the elliptic function of the energy, that's also an invariant. For the actual calculation, we also need the corrections, or the x naught to the -1 or the x naught to the -2. We needed them, we calculated them, and then you end up with a condition on the Stokes multiplier, so that when you go to the other side, you really exit the region of poles, that the thing calms down. So this is the equation that you get. There is an n, which is the total number of loops here, but it so turns out that the solution of this equation is unique, doesn't depend on n, because you get something like e to the 2 pi n. Never mind, you can solve it if I give you this equation, and the solution is indeed mu is square root of 6 over 5 pi I, as I said, independent of n. So this is the connection formula based on the property that the tritron here must be the unique one that has such a short region of poles. And this is a condition on the Stokes multiplier. And of course, the method applies to any integrable model with tritron K. And I'll end up, this is a paper that we published in Transactions of the AMS. Two comments. So you see, the idea is very simple. The proof is very long. It could have been made a lot shorter. But one of us, namely my student, rejected systematically the idea that we revisit the proof. So we were stuck with a longer proof, but it can be done in a much simpler way. And speaking of the central connection with Dubrovin, now I'm working with my student Nick, who is here, on providing a far shorter proof of the Dubrovin conjecture, still based on researches, but really short. And that's basically what I wanted to say in a nutshell.
Thank you very much. Okay, so we have listened to a lot of difficult mathematics, quite different one from each other. Now it's time for the discussion, free discussion. Before that, I would like to just raise some possible discussion points. Of course, everybody is free to raise any question or make any comments. But one point was already touched by Ovidio about the paper, which are very long. I think my papers on this subject are way too long, and maybe this is a problem. I think sometimes our paper should be shorter, and maybe we shouldn't aim at absolute rigor, because there are some details which are not that important, but just to fill them, we have to make a paper 20 pages longer. So this is a question, a discussion point I would like to raise. Another thing, which is like, if we are globally efficient, in the sense that in many papers we do a slight variation of the same things, like this Boutroux curve is spread many papers, but there is not a single paper who does the full theory. And so again, we are replicating in our papers that are becoming longer and longer the same details. And the third discussion point is about the exact WKB method, which is a method was not presented, but it exists. And I would like to know from people working in this area, what are the rigorous results that they are getting. Okay. So please interact and raise questions, make comments.
Hi, Davide. Ciao. I wanted to. I was going to ask you something technical, but then I wanted to respond immediately about your thing about gappy lemmas and things. And I mean, it's a good point. I mean, I think as mathematicians, you know, we become obsessed. We become maybe self-obsessed, but we become absorbed in these, you know, technical details, and sometimes we gain a lot of enjoyment from these very obscure technical lemmas. But you're right that, you know, maybe nobody reads that in the end, and also maybe there is a gap that we didn't see, and the referee doesn't read it properly either. I mean, I wonder, can computers check some of these things now? So that recently there was a talk in the BAMC, you know, British Applied Maths Colloquium. There was a, now I should remember who it was by, I forgot. but anyway, there was a discussion session. There was a discussion about you know, getting computer assisted proofs. And obviously there are these big programs, and in things like algebraic geometry, maybe some very axiomatic things in topology, maybe in some areas, it's in some parts of algebra or topology, algebraic topology, maybe it's easier to automate some of these proofs, but I don't know. I think maybe I think analysis is a lot harder. I think
it totally can be done. I mean, if you bring your proof down to the level of ZFC with all the details in that language,
yes,
totally.
Yeah,
but
it can be.
Then I think you have a few tens of thousands of pages.
But it's a big job. It's a big job, isn't it? I mean, somebody.
Yeah, I think it's an impossible job.
I think it's impossible. And also, I mean, I have here this beautiful book from the 50s, which is called ARA Transcendental Functions. I don't know if you.
Oh yeah, yeah.
Okay, I bought it from the Imperial College, who dismissed it, and it's 300 pages. There are like thousands of results and formulas. And maybe our paper, which is 70 pages, would be one line in this book. So I mean, the complexity is becoming too big to handle, and some things. So I mean, asymptotic analysis is pure mathematics, but it's also applied mathematics. As a subject of applied mathematics, you don't need all that rigor, I guess. Mm-hmm. And if you want to do a book like this, you cannot do it. I mean, now there is like the online version with Peter Clarkson wrote for Painleve equation, but it cannot be so thorough as this book, because nowadays we are writing too long papers, I think.
Mm. Yeah. Okay, just a completely different thing. I just wanted to ask you quickly about the lax pairs that you use for your analysis, because of course there are many different lax pairs that you can use for Painleve equations. So how important is the choice of lax pair? Because, for example, you mentioned the matrix form gives you this trivial connection, on a vector bundle, and then you have also this other connection, which is if you take the scalar form. But for me, that's not the lax pair that I would write down, or naturally for Painleve 1. So I'm just wondering, for example, the way I would do it is take a reduction from KdV, and then you would just have the spectral parameter would just appear as the eigenvalue and so on. And so I'm just wondering how important is the choice of lax pair in this story. And
well, it is important because even though everything is equivalent somehow at some abstract level, then when you in computation it is not. I mean, like for the roots of the generalized Hermite polynomial, we have three different characterizations in terms of three different harmonic oscillators. I suspect that there is some kind of abstract Laplace transform that connect the three of them, but and maybe abstractly it is trivial, but down at the level of computation makes a lot of difference. Maybe you arrive to formulas that you are unable to show that are equivalent. You know that are equivalent by principle, but when you work of them, you look at them and they don't look equivalent at all. So somehow it is important, the choice. Like, for example, the people working with the depth-2 method, they don't like too much the singularities. Okay. So, for example, if I remember well, one paper by Peter Miller about the rational solution of Painleve 2 is using another approach. So, am I correct, Peter? Where somehow you avoid the singularities that you get from. I mean.
Right, you can turn poles into zeros, of course, by some Pequin transformation, and then you can deal with it that way, right? Just to say something about the different lax pairs. Of course, there are many of them, and like for Painleve 2, the famous ones are the Flashka-Newell lax pair, which I think, as you were saying, comes from MKDV or something like that.
Yeah.
And then there's the Jimbo-Mewell one, which has been identified as some kind of Laplace transform of the Flashka-Newell one, and vice versa. So there's some connection there, but it's not so direct. It involves Laplace transform of the spectral parameter.
Yeah.
But both of these have been used by these kind of steepest descent type methods to get the results. Like the Flashka-Newell one. It has not directly been used to study like poles of rational Painleve 2 solutions. However, it's the same Riemann-Hilbert problem in disguise as this orthogonal polynomial one that comes about from the Bertola-Botner method. You can map them onto each other pretty straightforwardly. So that problem can be analyzed in that approach or by the Jimbo-Mewell method. And the interesting thing, I guess, is that I think it's true, if I remember correctly, from the Flashka-Newell perspective, you get spectral curves of higher genus. So there's some kind of squaring map that's happening.
Oh yeah, it's a double cover, I think.
Double cover, right? So you end up with like genus 4 instead of, or genus 2 instead of genus 1. There's something like that.
That's
right.
Right. Square of the spectral parameter. That's right. Yeah.
Right.
Yeah, that's right.
We've killed it now.
I'd like to ask a video question if I could. So I wonder if can the approach that you described work for truncate solutions, or is it just you need the tree truncate? You have to kill the poles as big as.
It does. Yeah.
It does. Okay.
The thing is, I mean, if you're looking for the same kind of connection, infinity to infinity, the Stokes multiplier will be the same.
And
And
you also
it
mentioned
should work actually as a general method for the generic solution of P1. So you can follow it all around, and then you have a more interesting structure of connections.
I see. So, but I thought I understood that you needed some sector where you had analytic behavior to start with, and then you can go from there. No?
No, not necessarily. So the tritron key is unique with this interesting property that it has a short sector of. But otherwise, I mean, you can go full loop, and then the condition is one of single valueness.
I see. So is that where the integrability is coming in, or
Yeah, totally.
Okay,
I mean,
I see. I get
the thing
it.
is not integrable. You will get a complicated Riemann surface of singularities that is sort of in an inextricable mess.
I see. Thank you.
Just before I forget, because we were mentioning several references. Is it possible to get the PDFs, because the PDFs of everyone's talks had references, and I would add them in the reference repository because it would be very useful to just have access to them, if it's okay.
Totally on my side, yes.
So if you don't mind, it's just
Yeah, fine.
yeah. Sorry.
How should we send them to you, or I mean, how should we get you the slides?
Yeah, just send them to me whenever you.
Can you put your email in the chat or something?
Yes.
Thank you.
Mention this because there's the different approaches, and there's definitely several of the papers that I actually didn't know, and I would really like to go and see. So, sorry, let me just. So I just put my email in the chat. There.
I have a question about these WKB problems with the apparent singularities. So if one actually considers the WKB analysis, the periods of the WKB differentials, because the monodromy representation of the Schrödinger operator is the same as if just forgetting about, at least in PSL2, is the same as the one that you get by just forgetting these apparent singularities. So if I compute the WKB periods without the apparent singularities and with the apparent singularities, in principle, they should be same, at least in PSL2, because at the end, these are essentially Fauconcherov coordinates for the monodromies. But they're very different if one actually computes them, because in the case with the apparent singularities, for example, S odd has also even powers of each bar, because you have additional terms in the projective connection. So how is this?
Well, if you can find the computation in this archive paper, I mean, the appendix of this paper by Tom Bridgeland and myself. And well, actually, if you do the computation from scratch, and then these things will disappear. When it will not contribute to the monodromy. I mean, it's something like it's really since something which is, let's say, something discrete which is asymptotically exact, then will be exact forever. So in the if you do WKB, then this apparent singularity will not contribute to the projective monodromy.
I see. So in the end, when one computes the periods, at least in principle, all these
just because like the Stokes complex do not depend. I mean, you separate the potential in various parts. So the Stokes geometry just depend on the dominant term of the potential. Okay. to the cubic oscillator, and then you will have a correction, okay, which will be of order h to the 0. I mean, and this correction you compute it, and it will vanish. Okay.
I see. Okay, thank you.
I would like to ask maybe some ignorant question. So the question is the following: if we study cosine or hyperbolic cosine potential, and we want to find its spectrum, then the spectrum is governed by some special one-parametric solution of the Painleve 3 equation, and this solution is distinguished by the fact that it has some series looking a bit like Trade, so it terminates in one direction. So I wanted to ask: is there the same situation for other Painleve equations, like 1, 2, 4, or not?
Well, let me say yes. I mean, like when you have like an eigenvalue problem, it's just each eigenvalue problem that you have, it's like the vanishing of a Stokes multiplier. Now you can connect the existence of, like for Painleve 1, you can connect the existence of pole at infinity with the Stokes multiplier. So the Trade solution will be the vanishing of 2 Stokes multiplier, and the Trunke family of solution will be related to the vanishing of 1 Stokes multiplier. And well, I'm not an expert of many, I mean, of many Painleve, of all the Painleve equations, but I would expect more or less the same, I mean, some phenomena like this for all Painleve equations. For sure in Painleve 2, well, yes, but I don't know the details, but I would expect it, like that the vanishing of 1 Stokes multiplier correspond to some very peculiar asymptotic or the corresponding solution of the Painleve equation. And for sure there are results in the literature about that, but I don't know the details of all of them.
Thank you. So what should be the intuition about this? So how to understand? So if you have several Stokes multipliers which can vanish, what can be possible implications for the form of the asymptotics of the Painleve equation? So if just one Stokes multiplier vanishes, does it mean that we can have some tau function which is kind of a one-side series, defined not only on the line but in some sector?
Yes, I would say so. I would say so.
I mean, I know in the case of
Thank you.
in the case of Painleve 3, there's some solutions where all the Stokes multipliers are 0. There's just a connection matrix in the problem, and those solutions are they're analytic at the origin, which is unusual for Painleve 3, right? Which typically has this branching point.
Yeah, I have a quite general question, and I think the experts here must know immediately. So, in some sense, I mean, these oscillators that appear in connection with Painleve equations are integrable because you can reduce them to Painleve equations in some ways. And I wonder what if you take all the Painleve equations, maybe P6 is special, though I know that it was studied by Nikita Nekrasov and Lukianov. I think they found something very interesting. What type of oscillators do you get? Do you get more than cubic and quartic? Is there anything else higher sort of power of the polynomial?
You get Hoyne equation.
Hoyne equations. Okay.
Well, to get, for example, the odd oscillators, you take the hierarchy of Painleve 1, and the even oscillator, you take the hierarchy of Painleve 2. So
right, but do you go beyond? Do you get something beyond cubic? Is there anything which is quintic or what?
Yeah. You take the second equation of Painleve 1 hierarchy, and you get the quintic oscillator.
Okay, interesting. Okay, but that's very interesting. Yeah.
I mean, it's a game you can play, but then there are so many parameters. Then you keep. I mean, you get lost in the complexity of the problem. But it's a game you can definitely play. I don't know how interesting it is eventually, but it is for sure possible.
So I've got a question. Maybe it's related to Davide's presentation. So, you know about this preprint of Shapiro and Tatar about there's some quartic oscillator that they're studying, and they find that there's a parameter, and when the parameter is selected such that there's a double eigenvalue of this quartic oscillator, then those parameter values appear to be very close to, but not exactly equal to, the zeros of these Jablonski-Vorobiev polynomials. Do you have any thoughts about that?
Tamara was here. She left, but a student of Tamara who was also in the audience is working on that. But I think they already left. No, I mean, sincerely, this, what do you call it? This branching point of oscillators is something that I still haven't understood. But I'm pretty sure that somehow, if you do the WKB analysis, they must be related to Boutroux curves. Okay, maybe add other quantization conditions, but still on Boutroux curves. I think that there are some results by these French people from Angers in the 90s. They studied the branch point of cubic oscillators. There is this old paper by Bender and Wu. They do the branch point of the quartic oscillators. I think that if you understand, I mean, if you can put them to rigorous, I mean, I don't understand them yet. If I would understand them, then with this technology of the Boutroux curve, I would be able to compute asymptotically that thing. I'm pretty sure that it is related to some Boutroux curve.
I mean, I guess you can ask lots of questions about special values of a parameter in your quartic oscillator where something happens, like a branching point for the spectrum, or when there's an eigenfunction of a certain type, like in your work and so on. And what's interesting, I guess, is that some of these conditions correspond to, like, poles of Painleve functions, and other ones are close, but not quite, right? For the same oscillator, right?
Yeah, but to be, I mean, I think I've read most of the literature on an harmonic oscillator that has been published in the 20s or 30s, and it's huge and it's a lot of things, but it's really too big. I mean, but for sure there are a lot of very interesting phenomena, but not all of them are related to Painleve equation for sure.
And then I'd like to make one comment about your proposal for discussion about making the papers shorter, which is that those of us working in steepest descent for Riemann-Hilbert problems are waiting desperately for Percy Day to finish his book, in which he's going to lay out all of the parametrices that are needed for these problems, so we can just cite it and then be done with it. But until that happens, we have to just reproduce the details in all of the papers because there's no fundamental reference, like you were saying. So,
So maybe I have one more question. So do I understand correctly that usually when you study harmonic oscillators, you do not care about self-adjointness of the operators, and some that they can be complex and so on. Is it true?
No, for sure, you don't care too much about that, because you have poles in the complex plane. Like, for example, even though your solution is real, and you will have real solution that maybe correspond to self-adjoint oscillators, then you will also have complex poles, which are for sure related to non-self-adjoint operators. And the important fact is that if you do WKB, then you know if you study, like you have a spectral curve, and then somehow the real oscillators correspond to real spectral. I mean, spectral curve with a real structure. But then, like the Boutroux structure, for example, is more general than that, because you can have a curve without real structure, but which are Boutroux curve. So, indeed, what we are looking at is something more general than some real structure or self-adjoint structure.
Yeah,
Thank
I
you.
mean, in terms of compactness, because you asked about it, I mean, we have polynomial potentials, and because of the growth at infinity, of course, the resolvent is compact. Whenever you meet the conditions of self-adjointness, if you have a quartic oscillator, real parameters, that should be self-adjoint on the real line. But as Davide said, is not very interesting from the point of view of Painleve, this self-adjointness.
Thanks. So I want to ask maybe another question. So if we decide to impose this self-adjointness condition, will there be any zoology of this self-adjoint operators? Maybe not only of self-adjoint operators, but something which can be considered as a perturbation of the oscillator. For example, upside down quartic oscillator, or something like this, like that. Is there any description of all such problems? Maybe I'm asking about a kind of Hermitian operators. Like for Painleve S3, there is only a cosine and a hyperbolic cosine potential. And what is the situation, for example, for Painleve 2 or Painleve 1?
Yeah, I'm not sure I got the question about the perturbations. So what would you like to know about the perturbations? I mean, I don't think if you perturb them, I mean, you preserve all the sort of niceties from the point of view of self-adjoint operators, but probably they cannot be linked back to Painleve. I mean, they would result in non-integrable stuff. That's my expectation.
I'm asking something like this. For example, we have cubic oscillator. This cannot be self-adjoint operator because it tends to minus infinity in some direction. But we can consider it as a perturbation of quadratic oscillator, and probably we can even consider several different regions of this potential, like near the top of potential and near the bottom.
Well, it's a singular perturbation. If you start from the quartic, you basically eliminate the fourth power, so it's not a nice perturbation.
Maybe I can ask this in a little bit different way. So this condition that some stocks multiplier vanishes, do they correspond to different variants of the spectral problem for the same potential or not?
So I haven't understood the question. Do they correspond to the same?
To the some different spectral problems for the same potential.
I think your audio, you froze while you were speaking. Your camera froze. I couldn't hear.
Do you hear now?
Yeah, now I hear. Yeah.
Yes. So the question is, there are these conditions when some Stokes multiplier vanishes. Yes, and there are a lot of such multipliers, and do such conditions correspond to different variants of the spectral problem, probably for the same quartic oscillator, or for whatever potential we have for given Painleve equation.
Yes, it is always the same oscillator. You just imposing different boundary value problem, but the oscillator is always the same. You just the choice of you have a lot of choice of possible boundary value problem, and every choice corresponds to a different family of solution of the Painleve equation.
And is there any description of all such boundary value problems which are possible for given potential for given Painleve?
Yeah, basically you can, if there are two kinds of boundary value problem. One would be the lateral boundary value problem, which is imposing the vanishing of solution in two non-neighboring Stokes sectors. Okay, and then you would have the central boundary value problem, which would be choose the origin and then a Stokes sector and imposing a boundary value problem. Okay, so all of these have to do with distinct possible special solution of Painleve equation. I mean, the classification is very simple.
I see. Thanks.
There's a question from Andre Voros to you, Davide.
Yeah.
The Stokes multipliers of the linear cubic oscillator from Sibuyu's book, 1975, chapter 5, 27, obey the same functional equation as the Stokes multipliers of Painleve 1. Example, Kapayev, 1989. And then it's the information. Does your work explain that? Can you relate those two sets of Stokes multipliers?
Yeah, let me say. Well, the Stokes multipliers, if you fix the equation, they satisfy just an algebraic set of relations. Then if you put in some parameters and the Stokes multiplier will be entire function of this parameter, and this would transform the algebraic relation into functional relations, but they are really the same. So I think these are just the same equations.
Davide, can I ask you a question?
Of course.
Yeah. So sure. Do I understand? Is it right that the quartic oscillator, for example, that you're looking at for one of these, say for one of these problems, is what I would get if I took the matrix differential equation in the spectral equation in the lax pair, the matrix lax pair, and just eliminated one of the components? Is it the second order equation that I would get, or is it a different thing?
Yeah, it is really the same.
I see.
I mean, there are always two choices of. I mean, there are two choices, but once you stick with the choice, it is the same. It's
okay.
Just,
so it's a the scalar representation of the.
Just the scalar. The nice thing, I mean, about the scalar is that the scalar equation, it's really a normal form under gauge transformation of a matrix system, and so there will always be a representative. While when you do the matrix system, then you are choosing a normal form, which is not a true normal form. That's why it will not exist at the pole of the Painleve equation. Because like there is this big theory of Hoppers by Drinfeld and Sokolov, and they really show that whenever you're working with a connection on a reductively algebra, there is a normal form, and this normal form corresponds to these Hoppers, which are just scalar equation for SL2.
So this is the application, by the way, that you're discussing. You mentioned on your slide this. You cited the Bertola-Tavbis paper. So they're using this fact that somehow you can, transform away the poles, right?
Yeah, exactly. Because the limiting scalar equation will exist, and that's how you can factor out the pole by the gauge transformation that we send to.
I see, but everything there, you can lift it somehow to the matrix problem. It's just maybe less obvious. Would that be true, or?
The fact is that the matrix problem, as it is written, does not exist in the limit of a pole, because it's just like the point where this. I mean, as far as I understand it, it is that particular point where the normal form we have chosen does not exist.
So it's bad coordinates, really.
Well, yeah, you may say that, yes.
Can we try to say it in a bit another way by saying that evaluation of the tau function is precisely where the inverse Riemann-Hilbert problem doesn't have a solution. So we cannot write a second. We cannot write 2 times 2 linear system with a given monodromy.
Thank you.
I have a question about the Tron series representation of the tree truncate solutions of Painleve 1. So is there a way to understand? So is there a similar expression for general solutions? Or can you maybe say a bit more about how do you construct such a series representation?
So I didn't get the first part of the question. I mean,
the first part of the question was that you had a series representation for the tree truncate solutions of Painleve 1. Can you write something similar for the general solutions?
Okay, for a transseries representation can only exist for those solutions that have some sector of analyticity. Otherwise, you can have a more generalized sort of asymptotic expansion in terms of elliptic functions. I mean, that's kind of the Boutroux type of, but that's not a transseries bona fide. Now they match I mean, from the sort of trans-series of the truncae or tree truncae, you can get the other one. I mean, that's what we did in one of the papers, but it's a different type of expansion when you get into the pole region.
Okay, can you maybe explain a little about how you are getting these series representations?
The trans-series representations, okay. So these are really gotten algorithmically. So first of all, you look at the asymptotic behavior, say, of the tree truncae.
Mhm.
And you have a leading order, and then you are looking for a correction to the leading order. Then you see that you have a power series, and you can insert a power series with unknown coefficients, get a recurrence relation that generates the power series. Now we know that if the power series diverges, and this is something that you can check, for instance, based on the recurrence relation, in the Boutroux variables, there is exactly a factorial divergence. There is always a small exponential lurking behind. So then you look for further solutions in the following form. You take the series plus a delta. The delta should be an exponential, and indeed to leading order you get a linear equation for delta, which gives you the leading exponential. Now that you know what to do, you write a formal trans-series solution, also with unknown coefficients. You plug it in, and you mechanically get a sort of a recurrence relation for all the parameters of the trans-series. And this can be done for Painleve, but it can be done for any system of ODEs.
Mhm.
So that's completely algorithmic. I mean, you can find that. I mean, if you look at my Duke Math Journal paper, not this one, but the one in '98, in which I proved Borel summability of the general trans-series of ODEs, or maybe even the IMRN paper that precedes it, that's easier to read. That's IMRN, I don't know, it's the Duke is something still like 98. I don't remember the year by heart, but there is an old paper. I present this machinery in detail. How do you do it? It's also in my book on asymptotics and Borel summability. I mean, really a step-by-step guide on how to get the trans-series in general.
By the way, maybe continuing Helene's question. So, what would you say about the generalization of the trans-series, which is not in the power of e to the minus x, but in powers of e to ix, which lives only on one line and continues in both directions. It cannot be called trans-series in any sense, or it's something very different.
I mean, technically, the trans-series introduced by Cal were real valued with real parameters. But subsequently, we extend this trans-series indeed to the complex domain. There is a condition, of course, that those exponentials, if they are purely oscillatory, they are guarded by some powers of x, so that the whole expansion is still an asymptotic expansion. Indeed, for Painleve, you would have a two-parameter trans-series, and you can see sort of the details about this trans-series in a paper by Alexander Ritz and Stavros Garoufalidis. So they look at this oscillatory trans-series. If you fail even this condition of sort of decaying, making the whole combination package decay, then you get inside the sort of range of my Invenciones paper, and then there are singularities of the actual object. So then not only the representation fails, but the solution fails to be regular. So that's the limit. Purely oscillatory, guarded by powers, so that they still decay.
Thanks.
Sure.
So I also wanted to ask, so I have understood correctly that there was a statement that if we want to sum this time series, which was one-sided, we can perform a Borel summation of each coefficient in front of xi to the power k, and this Borel summation will give us finally the solution of Painleve equation.
Correct. Yes.
So,
yeah.
So does the same apply for this bilateral transseries with oscillating psi?
Yeah, sure. So, and that is also very general. So if you look at either my IMRM paper or the more general Duke Math Journal paper, so there the transseries are used to that limit when they become oscillatory, and this summation survives, and the general solution of an ODE that has some region of analyticity can be written uniquely as a Borel sum of a transseries. There is a caveat. I mean, there are special directions, the Stokes directions, where the transseries changes, and along those directions, usual Borel summation fails, and one has to replace it by the much more general Ekal Borel summation. So there is a way, and in my papers I use something different. I create a space of distributions, and you can forge through the singularities. That is not called classically Borel summable, but closing this parenthesis, that's how you get the general solution of these ODEs, which decay in some direction.
Thanks. So, and is this a structure of singularities of the Borel transformed function is known? Is it complicated or not?
The most interesting thing here is that these ODEs are at their simplest in Borel plane. The structure of the Borel plane is amazingly regular. So from the ODE, we know where the singularities are. They are exactly equally spaced, so they are periodic, and there are a few periodic rays of singularities. So they are discrete singularities, periodically spaced. The spacing is dictated by the linearized ODE. Not only the position can be calculated from the ODE, the exact type of the singularities can be calculated. And if you want to reconstruct the solutions, even numerically, of ODEs, that's the place to start, the Borel plane. That's the most regular, even for P1, even for integrable models. Furthermore, in that space, all the series are now convergent. And at each singularity, you have convergent series. So that's a much friendlier space, and it's called the Borel plane. Yeah.
Thank you very much.
Sure.
Actually, can I ask a question also? Is there any known result which relates, for example, singularity in the Borel plane of Painleve 1 to singularity in the Borel plane of the cubic oscillator? Or in general also, I don't know, the Painleve 2 and the quartic?
Yeah, well, I mean, that's an interesting question. I've never thought about it. Maybe I'll talk to Davide and see how that goes. So let me not give you any rushed answer. There is time to revisit your question. It's a very good question. Okay, that's all I can say.
Thanks.
Given the time, perhaps we can stop the recording.
All right, I'll just stop the recording now.